All right, can you hear me? Okay. So I just turned off exercise 1, which we had up until now to do. And then before we leave this class, I will initiate another exercise, which you will have until Friday to do. All right, so as we discussed in this class, we are going to introduce topics and of course with examples, Mondays and Wednesdays, and then Fridays, both sections, I'm gonna solve problems. And I'm gonna solve different problems. So if you are in your section, you will see what I'm doing, but then also I would suggest to watch the video from the previous section, specifically on Fridays, because the examples will be different, all right? Just so we have more time. Otherwise, an extensive, detailed example, you can do at most 2 in 50 minutes for the first time. And then, so at least we'll have 4. Office hours, as we said, normally I have office hours Mondays and Wednesdays. Sometimes nobody shows. So sometimes it goes down if there's no activity in 1.5 hours. All right. So if you go towards the end and you don't see anybody, that means nobody joined and it went down on its own. So Zoom. Usually I'm expecting more people to come. So specifically today, as an exception, my office hours will be from 4 to 5, not from 3:30 to 5:30, because I have one meeting with people from other states for the research before and one after. All right, so 4 to 5 are my office hours today. And then the next set of office hours will be on Sunday. Primarily, I know, usually it's for homework related and other questions. Okay, any questions about that, just to remind you? All right, the other thing I want to remind you, that if you want to know what we've done in class and what you're supposed to do, my advice is to go in this week's, for example, module. And you will see after every day, so for Monday, and I will do the same thing for Wednesday, I put down the specifics we covered in abbreviated form and what you need to do to remind you. For example, here it reminds you to do exercise 1 by Wednesday before the lecture. All right. So tomorrow or today, I will remind you of that exercise and I will start reminding you of homework. All right. So, and then I will cover, so nothing extensive, just so you remember the specific things, because a lot of you are asking me. So that's the place to find it. Okay. Any other questions? All right. So what we will do, as I would normally do here, is to go to today's lecture. If you see what we plan to cover. All right. So we go here. And the plan for today is to talk about primarily vector operators and show you space and coordinate systems and relations between coordinate systems. These are things that you have seen before, but I just summarize them. So you have them here. However, your book, as I reminded you, part 1 of your book, which are pages from 1 to 108, is a very detailed review of vectors, of coordinate systems, of vector properties, and of how you take the various operators in different coordinate systems. So these are things that I don't want you to memorize, but these are the things to use if you have to solve a problem as we move down this class, since I don't expect you to remember those kinds of extensive formulas, all right? What I will try to do in class is try to connect what we do using math to the physics that you have to learn, all right? And because it's physics that you have to learn and apply. Math is a way to write in concise form of what the physics tells you. It's not like the goal. All right, it's a tool. It's like somebody wants you to read Shakespeare, and then you have to understand the vocabulary. All right, so you learn the vocabulary, not to stop there, because nobody's going to ask you about the vocabulary, but they will ask you about what you learned through whatever sections of that manuscript. So that's how exactly it is here. Okay, so I will try to do the best I can in terms of connecting, and every time we're going to do an exercise, I will never give you as homework a mathematical exercise. I may do it here as an exercise on TabHub, just so that I help you with a review, all right? And we don't have an exercise like a yes, no, and so forth. It's not solving an important problem, but the homework is going to focus on the topics of electromagnetic fields, for example, and so forth, electromagnetic, and what are those fields? How do they translate into circuit quantities? All right, because a field is an abstract concept. The bottom line is you have to design things to either generate those fields, so antennas, or in this class, you will have to take the knowledge of the fields and then translate them into circuit equivalents. So we'll talk about that. All right, so now to finish with vectors, I will start with vector operators. And for that, I'm going, you have them in your notes. I have them here on Notability because I want to write a few things. So I wanted to tell you that there is one vector which is called the, in fact, excuse me, there is one operator that is called the del operator. The del operator looks like an inverted Greek delta and is a vector. And the del operator is an operator because it cannot stand on its own. And when I write it, you're going to see it. It has, in the Cartesian coordinate system, has 3 components. So the second, a sub y, theta, theta, y, and a sub z, theta, theta, z. Now you can see why it's an operator and it cannot stand on its own independently, because there is no meaning to this unless this operator operates on a function. And because it's a vector operator, the way it can operate is in 3 different forms. All right, so if you have, now this is the del operator, del operator. Now, the interesting thing about this operator is every time it operates on a quantity, it acquires a different name. So when there are 3 ways of the vector operator to operate in quantities. One is to operate on a scalar. Let's assume scalar is temperature for us. So it operates on this vector. When it operates on a scalar, then this is called the gradient of temperature. It's not called the del of temperature, it's called the gradient. All right, and practically what that will give you, this is a sub x theta t theta x plus a sub y theta t theta y plus a sub z theta t theta z. And what does that really give you? It tells you how temperature, which is a scalar quantity, how it changes along 3 different directions. And why is that important? Have you seen anything like this in your everyday lives, where you have seen something? I will just make the connection. You have seen something which is very familiar to you, which in fact is just the gradient of temperature. And can somebody tell me when and how you see that thing every day? Do you worry about the weather? It isn't the weather forecast, but which of the things that they show you or tell you is the gradient? it may not necessarily move, but it is this colorful map, even static, that shows you, of course, if they move, of course, is how it changes over time. All right, that's the movement. Movement is time. But what it shows you, even the static form, say when, for example, we have cold weather, right? So say Minnesota, and you see something a dark blue, and you go down towards Chicago, and then you see some lighter blue. There are some sections that have still very dark blue, and others, that they're light, and then eventually becomes yellow. And eventually, if you go further down, might become red. And it depends on the time of the year. You may have very hot red spots. All right. How do they get that? They assign colors to the values. All right. And also, so for example, very dark blue is like negative. But they don't show the value. They show the way it changes. All right. It's not the absolute value that you see there. It's the way that there is a change across the US, for example. All right, a special change. And of course, they have it down to the ground, not higher. So there is only the change. And if, for example, we use a Cartesian coordinate system where Z is along the vertical direction, so it's XY, assuming that we are flat here, we'll measure down the planes, all right? Okay, so that's what you see. You see the gradient of this without the variation along the vertical direction, because obviously, every time you go up, it gets cooler, with exceptions of some tornadoes and stuff, some places where temperature inverts, somehow, but in any case. So all on the surface. And you see that. And what happens then? Old days, when the colors were not that vibrant on TV, and it was dark, you don't even remember that. But there was a time when TV was black and white, as a matter of fact, if you guys need to know. And it was not in the history book. It was kind of very recent, in my life. So in black and white, it's very difficult to see the variations of temperature because the scale, is not that great. So what they were doing, additionally to the gray space, they would have also those lines. And those lines will be similar to what even you see today when people are looking at, especially civil engineers and architects, when they do a mapping of a region and there are hills and there are kind of mountains and stuff. They are going to do these lines that they show you, not only what the peak is, but how it changes on every side of the hill. So sometimes the lines will look, for example, if there is a hill, you will start something like that. And if the hill is symmetric, you're gonna see something like this. But many hills are not symmetric. So sometimes you're gonna see something like that. And then you're gonna see something like this. And what you understand is that the hill is steeper here, because they show you how the derivative changes, and the closer the lines, that means that the steeper the change. And that's what we do. What you see is the gradient of the temperature, not the absolute. All right. So that is an important thing to remember. So we see that, but mathematically, it's this. Now, let's go now to, here, so you're gonna see here, I'm not gonna repeat it, is how you write the gradient operator in not only the Cartesian, which I wrote, and it's simple, but in cylindrical and spherical coordinates. And there is an example underneath it, if you wanna just do it for it. As an example, read this. Okay, this is a mathematical example. So, I would say, let's go now to a different type of to the same operator, but it applies in a different way on functions. And we call it the divergence, all right? The divergence operator. And it's still the del operator, But now, as a vector, it applies on a vector as a dot product. All right, so in a scalar, it was like the del, the scalar, but on a vector, it cannot apply in the same scalar product because you cannot multiply two vectors in scalar form. There's nothing like that. All right, at least that we are using here, unless we want to start working with tensors, which we are not going to do. So obviously, the only product between two vectors for us is like this. And that then is called the divergence of A. So now the del operator changed its name. Okay. And in this case, if it's an inner product between two vectors, what is the divergence of a vector? A scalar function. All right. So it's not going to have a direction anymore. So let's see what this is going to give. It's going to give the inner product between the del and this vector, which in fact, I will write it also. I'm sorry, this okay, this is a bad habit of mine, because I need to remember to write this as a unit vector. Please stay consistent, just is that when I go on autopilot, bad habits come back. So this one. All right. And then the inner product between these two vectors, what does it give? Theta A sub x theta x plus theta A sub y theta y plus theta A sub z theta z for the Cartesian coordinate system. So the divergence of a vector, all right, is giving us a scalar. Now let's try to see what that means. And I'm gonna go, I will start with something also that we do, and we've been doing forever in our lives, which is how our brain is thinking, because that explains how the brain processes things, all right? It's not, those processes are not like something totally independent on how we perceive things, all right? You remember that. The way we perceive physics and nature and the way we have defined science is absolutely correlated with the way our brain processes information. All right, we cannot escape that. Do you understand that? All right, the way we see, the reason we see like what we see, and another species from another planet, it could see all of us in a different way. The way we see us and the colors is because of retina and how the retina in our brain process the information. All right, it's us. So that's how we understand the world. The same thing applies on how we see other things, how we see the planets going around, okay, how we understand gravity. I mean, our brain does that kind of processing, all right? So where do we make that kind of processing? So the question is, okay, now that we think like that, what are examples that we practice all the time that are coming from this type of processing? Let's talk about that. So let's think of what that does. What that does is looks at an entity and says how this entity changes. What are the areas of a fast change versus other areas where the entity does not change? Because if the entity was a constant along our space, X, Y, and Z, what would the divergence do? Give us zero. So zero. And if there is an immediate change of, say, entity, of that entity, then it would be a non-zero value. And if this entity changes from one value to another value and then stays at that, what is going to be after that in the rest of the space? Zero again. So it shows only, gives you information about where the entity changes, but gives you zero information of in play about where the entity remains constant. Okay, so now let's think about that. So electric field is one kind of field where we're going to use this. Okay, but before we go to electric fields, which are kind of new to us, relatively speaking, let's go to other fields which are very familiar to us, which is optics and illumination. All right, an optical field. What I see you right now is like the result of optics. All right, optics is like an electromagnetic, it's like passive electromagnetic. There is a radiation, but in very, very, very small wavelengths, below a micron. So, but an optical wave from an electromagnetic wave, there is no difference after that. They're identical. But the optical wave is a very, very tiny wavelength, meaning it changes within a very tiny period of time. That's why we have good resolution. And I can see things down to a very small fraction of a millimeter if you're young, or if you wear glasses like me. All right. So let's think about that. So let's go from electric fields to optics. Okay. What I will ask you then, when you were a young kid and somebody asked you to draw the sun or a moon on the sky, how would you draw it? The sun, yes. For the sun, we will do that. So sun here. How would you do the moon if it's not a full moon? Something like that. That's not how they are on the sky. All right, each one of them has a different color and they're not like crisp like that. But what is it like our eyes do? It's only, we only write the places where the optical field changes abruptly. All right, so on a night sky, you see the moon and you see a light yellow inside the moon. It looks, it's not exactly, it's not exactly one color, but it has those shadows. Forget the shadows. When you are young, you cannot even process that. Your brain does not know what it is, so you forget it. Seriously. If the brain sees something but it does not classify it, you don't understand it. So young kids do not see the shadows in the moon. So like this, you are gonna do it like that. Yellow inside, black outside. And what do? You don't try to cover all of the, with, make the dark all around. You do that and everybody understands it's the moon. So practically, you do the divergence of the optical field. The same thing with the sun. Why do we put these rays? Because that's what, usually are there are two things, because of the atmosphere and how it comes, and because there are, the surface of the sun is not soft. It's not like the moon. There are a lot of explosions, and a lot of times those comes like they make that sense of it, of rays, especially under specific environmental conditions. That's what we do. Another thing I wanted to show you is a little more. So here I'm writing, of course, the divergence in Cartesian, cylindrical, and spherical. All right. So let me go and do some. Do you recognize that? That's a very famous part of the painting. Do you know where it's coming from? Yes, it's Leonardo.
It's original.
Yeah, is very famous, and of course, is God one hand and man on the other, and man is reaching towards God. Okay. Leonardo da Vinci, do you think that he was doing that the first time? He thought he was going with all of the colors every time he had a vision in his head and he was painting, and if he did not like the painting, he would throw it away. He was a master. A lot of times the colors were not even added by him. by his students. Like he was teaching painting and I would do whatever I had to do and I will ask you to finish it up. All right. But masters do great work because they think of what they want to do and they practice it. And when you want to practice, when you want to see, you have an idea on how to do something and you want to see how it's going to look, you're not going to start painting like that and waste all of your time. What are you doing? You do drawings. But what is the drawing? The drawing does not have colors, maybe some shadows just so you can see 3D, but practically only emphasizes the places where optically you see the changes between the hand and the background. All right. We do that all the times with cartoons when you draw something. I mean, the drawings we do, it's all of that. Now, we don't understand that we do this high math, our brain, but the brain is doing it. Now we found the brain does not know math the way we know it, right? Obviously. But we found a way to explain mathematically what is happening. So a lot of times, obviously the same thing we will see in when you go to electromagnetics. But let me also, to bring you closer to that, let me give you another example. So when you look in the sky at night, far away, you see stars, all right? So if I ask you to make a star, how are you going to make stars usually? Same thing. I mean, if you are a small kid, you will put something like that. And maybe you will do something like this, just to show that they're not quite, because they tinkle in the atmosphere does not show them exactly round, even if they will be round. You saw that like that. So at that point, all right, the star is the source of light, whether it's directly because they burn or because usually the ones we see from far away are the ones that are like our sun, they burn, all right? So it's a source of light. They generate light. And so when you start looking at the optical field around it, you don't see all the variations in there. First of all, our eyes cannot go that far, but even with a telescope, usually what happens is you see where the source is and nothing around it. All right, you don't see the other, nothing around it, but you see the source that produces the optical field. So it is very similar to like taking the optical field, which is like an electromagnetic field, but with very high wavelengths, all right? And then processing it so you find its divergence, which is non-zero at where exactly the source that produces it is. And you're going to see that. So if you have a charge instead of a star, and if the charge produces a static field instead of an optical field, the divergence of the static field, even if the field is going to change, and we said if you have a point charge, it's going to change as 1 over the distance squared, at least in magnitude, as you move away. When you do the divergence, the only thing you're going to see is like the charge that produces the field and 0 around it. So that are the things, all right, that we are doing in electromagnetics, but there are things that our brain already has done as we observe nature. So these are the kinds of things to connect what you see, you need to remember, and then use it with our personal experiences of what we are going to do in math is more than math. It gives us some meaning, physical meaning, and that's what we need to keep in mind, all right? So the last thing is when the del operator applies on a, let me see what time it is just to make sure. When the del operator applies on a vector, but with a cross product, then it's called the curl of the vector. So now the del operator applies on a field A. Okay, I called it field, is a vector here. And this is called the curl of A. And how do we do this? I mean, I'll show you how I remember how to do this for at least the Cartesian system, not for the other systems get complex. But for here, the del operator, of course, in the cross product, you have seen that already. You have here the components of the del. And then you have the components of A. Do you remember how to write this? So for the determinant, the way I remember it, start with X. So we start with this. Oops, not that, sorry. There. We start with this. Okay, so we have to write this component. And then, since we start with that, we remove this row, we remove this column. And then we have like a 2 by 2. The 2 by 2 determinant, I can do it, which is theta AZ over theta Y minus theta AY over theta Z. And I then remove this. And now I'm going here. So then I remove this line and this column. And then I have another 2 by 2. However, when I start this, I put a minus in front. That's how I remember it. And then I keep doing the same order in the 2 by 2. So I have theta AZ over theta X minus theta AX over theta Z. And then I remove this and this, the other. And then I go here, and then I remove this and that. And now at this one, I put a plus in front. Theta AX, theta Y, minus theta over theta Y over, well, AY, sorry. Theta X, theta Y, I made a mistake. Okay. So obviously here, what we see, what is the complexity here is that we get the derivatives of vector, practically the curl reduces to another vector that is a function of the derivatives of the initial vector A. So because this is a vector, right? But not in a simple way. So a lot of times you say, okay, why is this important? When I apply the del operator as a cross product on a vector, what does it tell me? If this is not 0, that implies that the vector has a rotational form. All right, so if it is an electric field, it seems that the electric field moves around like this, does not go straight. All right, the direction is not along one direction, but it has this circular kind of, it's not motion because you are not in the time domain, but it has this circular rotational kind of form in the space domain. That's all that it tells you, all right? If the curl of a vector is 0, then it goes straight. It's non-rotational. So having said that, and then of course these are the Cartesian, cylindrical, and spherical. So here, let's try to think. If the divergence of the, I should say, excuse me, if the divergence of a field, let's assume that A is a vector field, all right, is 0, what does that tell us? Then the field is not starting from a source. There is no source nearby, all right? There is no charge nearby. This field, somehow the charge is at infinity and has produced a field, all right? So the charge is on the sun and we see the field here. So we don't see any charge in our vicinity. So practically the field, if you're so far away, is gonna come like straight rays, all right? And why is that? Because if the charge is at infinity, and I am kind of a, small observer. So, and if the field around the charge goes like a sphere, as we discussed, I will occupy a tiny, tiny place on this sphere because the center of the sphere is going to be at infinity. So the radius of the sphere is going to be really, really big, which means that if the charge were to be, if this charge here, if I had a charge at infinity, and let's assume that this charge creates this sphere, so the electric field goes like that, all right? Out, we'll assume positive charge. The electric field goes like this, and it's constant on the surface of the sphere as we move along the sphere. So if I'm a tiny observer, because this is a huge distance, let's assume 10 kilometers, and I am who I am, I will probably be here like this, like a teeny speckle, which means because now I'm a teeny speckle on this sphere, but I have size on my own, what I will see coming to me will be this ray. But this ray, when it comes to me, are like multiple rays, all right? But they're all the same direction. When I'm here like this person, and there is only one ray that comes because I'm so far away from the source, it will seem to me that this one ray that I see here are multiple rays, but they have the same direction. Do you understand that? Okay. So when I go here and I see the divergence in zero, that means in my place, there is no charge. So the charge is very far away. So the field that I will sense is like straight line. There are lines parallel. When I see that the curl of this field is also zero, that implies that it's like a solenoid. There are no rotations. It does not go like that. So it will be straight lines going smoothly. At least in my space, they will look like this, what you see here. All right. Now, to see exactly when you see that, what you mean. When now I am in a space where I see the divergence to have a number of the field, that means that the source is near me. There is a point exactly where the divergence is not zero, and that is my charge. So I'm near there, which means that if I'm an observer, I will see that field, because if the charge is here and I'm here, then the field is going to come to me like that, but next it's going to be like this, and then it's going to have a different direction and so forth, all right? So if I am to look at what happens in my vicinity, this is what I see. But if the curl of that field is zero, that means that all of these rays will start from here, but they will go straight out, and they're not going to do any circulations or anything, all right? That's what it means. And usually what the book is called that is the irrotational. Now, I don't use the terminology to tell you solenoid, yes, because we use solenoid later, but so, and now you have a field that has, and those, let's assume that they are electrons, all right? So electrons that they are inside consider that as an observer rather, not even as an electron, observers. But assume that this field has a divergence which is zero, and then it has a curl which is not zero. A zero divergence means that the source is far away, all right? I don't see a source. However, when the curl is not zero, that implies that this field goes around. And usually fields that go around, which field goes around like that? That comes around and closes? The magnetic field. The magnetic field lines tend to have a curl. they don't have a divergence. The electric field lines look like that, all right, when we are close to the charge. They have a divergence, but they don't have a curl. And usually, if you are in electromagnetics, all right, it is possible to have either the divergence, it's possible to have both the divergence and the curl to be non-zero. So for example, you can have, all right, you can have a loop antenna. Have you seen a loop antenna? Like you have seen a dipole antenna, right? Have you seen dipole antennas? No? Okay, this one here has a dipole in there, but that's the problem with our phones. Where's our phone? There. Okay, that does not show. In some phones, you will see a gap here that separates the metal. Do you have a gap at the back? Maybe not. But some phones, they will have different types of antennas. This one has a wire antenna, but it's inside the plastic, you don't see, and it's curved, it's still a wire. Others have a loop antenna. A loop antenna, if it's like a wire, if there is a loop antenna, but it's like this. Instead, a dipole antenna is like that. All right? So you fit it at the center. A loop antenna is like this. Both wires, but they have different shapes. Okay. What these do is to excite different types of fields. So this excites an electric field that looks like that. Near field. This excites a magnetic field, and if the current on this go like this, and the current here goes like that. Okay, this here is a current. This excites a magnetic field that goes vertically from the surface like this. But the electric field does not look like that. All right, so the electric field is going to have a curve. So, but the magnetic field will not. So that's what the idea of having the divergence and the curl is to be able at some point when you see these values to get an understanding of how your field looks like. All right, that's all. And we'll do some exercises to see, all right, how to use those. So with that, I wanted to say that this is the material that we have. And also, going back, what I have added for you here, yes, we covered this. So now if I go back, we have also spaces and coordinate systems where I just give you a, things that you know, but this is one-dimensional, two-dimensional space, three-dimensional Cartesian, spherical, and cylindrical. Cartesian, cylindrical. So this is Cartesian. And the first one cylindrical, and then spherical. So that is the coordinates. And then what I wanted you to have access to is relations between coordinate systems, which also you have it in the book, but this is only on one document. All right. So we are going to use that when, keep it in mind that it's here. I want you not to memorize anything, just look at that to see what kind of information it gives, but we are going to use it while we are solving some problems. All right, so that's what I have. And the final thing that I wanted to give you is the following, to go now to here. Oh, not here. Forget about that. So, I said the wrong thing. That's what happened. Okay, so now wait until I. Okay, I have, so we're going to the second exercise. And what I want you to do is I give you a vector B. This is practice also. And you will have until Friday class time, all right? I usually turn it off like a few minutes, 2 or 3 minutes before we start the lecture. So here is, I give you a field in cylindrical coordinates. And then I want you to identify which of these A, B, C, D, E is the correct answer. All right, if we split this field B into X, Y, and Z coordinates, and we'll calculate those coordinates, I want you to tell me which of these 5 answers is the correct one. All right, so practice. And on Friday, I'll keep that until Friday. And on Friday, we're gonna solve problems on electric fields. How about that? Using stuff that we have introduced. Examples. Okay, any questions? All right, thank you. We'll see you on Friday.